Okay, let's now move on to the optical properties. There are several optical properties describing the materials. However, they are correlated each other. However, but it's a bit confusing for new learners how they are correlated. So here I want to summarize kind of these physical or optical properties. Okay. So first, we've just studied the polarization inside the material, which can be described by epsilon 0 chi e, right? So what we studied chi, susceptibility, is a proportional constant between the polarization and electric field. And well, on the other hand, the total polarizations are 4. Total polarization meaning including the electric field in the air or in vacuum too. In this case, we can describe the electric displacement like epsilon of 0 times E plus epsilon 0 chi A. And then we can make like this one as 1 plus chi E, and this 1 plus chi is summarized by epsilon like this. So this epsilon is a proportional constant between D and E, right? So which is called a permittivity or dielectric constant. This is also frequently used for as a material property. There's another important optical properties, which is refractive index. So let's see. In this case, when we think about the light wave with this expression, you have 0 exponential oscillating field of electric field in time and space. And this K, which is a wave vector. And this wave vector can be described by by 2 pi n over lambda x. Okay. So this n is called refractive index. Right? We often use in optics. And this n is related with dielectric constant or permittivity as epsilon equal the n squared. Right. So these are the 3 major optical or physical parameters related to the response to the electric field. Okay. So we studied 3 optical parameters, chi, epsilon, and n. And keep in mind that they have not only the real number, but also imaginary numbers too, as I shown in the Rorentz model. In the Rorentz model, we obtain the chi, which has a real part and the imaginary part. And meaning that epsilon is equal to 1 plus chi, meaning the epsilon also has imaginary part. And since the refractive index and the permittivity has a relation like this, just like this. So refractive index also has the imaginary part. So the question is a question. So what is the imaginary part of the optical properties? So this can be understood from the exercise after the lecture too, but I'll just briefly show how it can be understood. So as I mentioned, refractive index, people, you might think that n equal 1.5 for glass and water 1.3, like that. You never think about the imaginary part of the refractive index for glass or water. So, however, most of the solid materials, they have imaginary part. And just think about like this. So refractive index is made of the real part and imaginary part. And if you substitute it to the oscillating field, E0 exponential I omega t minus kx. As I mentioned, the k has the refractive, the wave vector has the refractive index term. So just keep in mind and substitute this one is by kx minus omega t, and k in this case lambda over 2 pi n plus ik. So meaning that it can be subtlety, right? Exponential minus I omega t, which is the temporal oscillation term, and the propagation oscillating term can be 2 pi n x. And furthermore, you have imaginary part of the refractive index. Don't confuse the wave number and the imaginary part of the refractive index. Now you have to multiply twice of I, so which means it's changing to the minus number, and 2 pi onto lambda kx. So now you can see that this term does not include I, meaning it's a real number, and so it's not oscillation. So as x becomes larger, this term itself is going down. So meaning as the light or wave propagate, gradually the amplitude is getting small, meaning that this is a decaying term by the propagation, right? So similarly, there's some there's some squared term, so it's a little bit not intuitive, but there's some relation between this imaginary part is mainly due to the decaying term, or in this case, the light absorption. So if you have some light absorption, you have the imaginary part of the refractive index.